Okay, everybody, I am in this video going to do GCSE Chemistry Higher Tier. It's paper 2 and it's from, actually hasn't got the year written on it. It says down the bottom here, 2021. So this is 2021 Chemistry Higher paper. Now this is the triple science paper, it's not combined science, but it will still be useful to you if you want to watch along. So, as if you've seen any of my videos, it's not going to get poured, it's not going to get edited, it's just going to be me going through this from start to finish. It's a 1 hour 45-minute paper. I would hope to do it in about, well, let's say 45 minutes. That would be my aim. With explanations, I've got a periodic table, got a calculator, got a pen, got a drink, ready to roll. So, let's start. GCSE Chemistry Higher Tier. I'm recording this in 2025, so it should be a useful paper for those who are just about to sit their paper 2. Right then, let's have a little look. First question. This question is about fuels and energy. A lot of paper 2 is about fuel, isn't it? Organic chemistry. Figure 1 shows the percentage of electricity generated in the UK between 2007 and 2017 using oil and using solar energy. Right then, percentage of electricity generated. So it looks to me, so oil went up in 2009 and then went down and decreased a lot. In 2007, there was effectively very, very little solar, and it is hugely increasing. It looks almost exponential, but we'll see what happens in a minute. Describe the changes in the percentage of electricity generated, so that's this, between 2007 and 2017 using oil and using solar energy use data, so I've got to use data. All right then, so I'm going to start off with oil. I'm going to say here that generally the trend is that oil has decreased. Oil usage has decreased. Now you need some data from, now it started 1.3 in 2007 to 2017, 0.5 on the percentage, all right, with a brief peak at 1.6% in 2009. All right, that sort of describes that trend, doesn't it? There's not a model answer for this, but it's like that's the general trend. Let's have a little look else. Oil, what else? Yeah, so I've mentioned there was a brief peak at 1. So I think I've mentioned 2 things there. General decrease and a little increase. Brief peak at 1.6% in 2009. Yeah, I think that's okay. Solar has increased from, now I'm going to say that's 0, that's just like about 0 to me, but they'll probably give you a bit of wiggle room, from 0% in 2007 to, what's that, 3.4% in 2017. That's only going to be worth 1 mark. I might just try and add something else. What else could I say? There was no change there. There was no change in solar usage between 2007 and 2009. They're both 0%. Notice what I'm doing here. I'm not hanging about. I don't know. This isn't straight off the specification. This is just to analyse this graph. I'm just trying to say stuff about this graph. I could say things like recently there was much more solar being used than oil. I could say lots of things, but that is definitely going to be worth 3 marks. I've got the mark scheme next to me. I'm just going to give it a brief check now. Okay, it's going to get it out. Okay, so let's have a look. Use of oil has decreased by 0.8, or from that to that. I actually wrote that. Yay. Use of solar energy has increased by 3.4, or from 0 to 3.4. That's worth 1 mark as well. So we need another one. Use of oil increased from 2007 to 2009. I did mention this peak thing. No change in oil use between 15 and 17. 13 to 15. Oh yeah, I could have mentioned it was the same there. And I did write solar energy, no change in solar between 2007 and 2009. Great. The point is there, if you're watching this, I just dived in. I wasn't thinking about, I used data. Notice I used data, I just put numbers in. Right, oil contains carbon and some sulfur. When oil is burned, the products of combustion may be released into the atmosphere. Explain the environmental effects of releasing these products of combustion into the atmosphere. Now then, I drew a little diagram here in our notes. If you're one of my students watching this, you'll know this diagram. This isn't what I would do in the answer, but it's just, that's meant to be a car, by the way. There are 5 bits of pollution that come from a car. Carbon dioxide, carbon monoxide, and carbon, in other words, the carbon pollutants. Nitrogen oxides, and what's the other one? Sulfur dioxide. When oil is burned, the products of combustion may be released into the atmosphere. Explain the environmental effects of releasing these products of combustion into the atmosphere, and it's particularly about carbon and sulfur. So I'm going to talk about these 3 pollutants and this pollutant. I'm choosing not to mention nitrogen oxides or oxides of nitrogen. So when oil is burned, explain the environmental effects of releasing the product. Okay, so environmental effects. So I'm going to go, firstly, I would talk about carbon dioxide. I would talk about CO2 being a greenhouse gas. What else would I say about carbon dioxide? I would say increases global temperatures, global warming. If you warm the globe, you're going to get climate change. What can that lead to? Polar ice caps melting, which leads to flooding. If you do geography, you're on a winner here because you're going to get loads of stuff here. Extreme weather, blah, blah, blah. Just say stuff about carbon dioxide. I think I've written enough there to get the carbon dioxide marked, I'm pretty sure. Extreme weather, animals and plants can't adapt, so they die off, whatever. Then you've got, I'm going to go carbon monoxide in my diagram, next one across. This is toxic. That's the only thing you can say about carbon monoxide. It's a toxic gas. It can cause death of animals. Okay. Carbon, otherwise known as soot. Now I would write these in sentences. Carbon dioxide is a greenhouse gas. It would lead to an increase in global temperatures, which causes climate change, which would lead to polar ice cap melting. So I would write it in full sentences. Don't look at this and think this is acceptable. Carbon dioxide is soot. Now I know that carbon is soot. Global dimming. It also, so this could, what would that do? Global dimming caused by particulates. Reduces sunlight reaching Earth. Sorry about my spelling, I'm not here. Reaching Earth. Don't really do much about the environmental knock-on effect of that. Soot also causes respiratory problems in humans. Sulfur dioxide, I would write about acid rain. When it combines with water, it would damage trees and aquatic life. Now, all I'm saying from this is you've got to know these. You notice how I said straight away, I know there are 5 types of pollution, and I am ready to just unleash words. All right, environmental effects and releasing these products. So I'm just going to unleash words. I think they're always going to run more on carbon dioxide. All right, so no stuff on this. I know that's enough to get me 6 marks. The mark scheme, I've got it all written in here. Just loads of stuff. Yeah, but notice it's revisable. You should have revised this. You should know there are 5 types of pollution. If you don't, try drawing this diagram up. 5 types of pollution. 3 carbon ones, a nitrogen one, and a sulfur one. Acid rain. Respiratory problems. global dimming, global warming, toxic. Watch that bit of the video, that's just useful. If you have me as a teacher, you'll know what we do on that. Suggest one reason why using solar energy is a more sustainable way of generating electricity than burning oil. Solar is renewable resource, whereas oil is non-renewable or finite. So that's it. Solar energy is renewable, burning oil is finite or non-renewable. Solar energy may not be able to replace the generation of electricity from fossil fuels completely. Suggest 2 reasons why. Now already this is a little bit outdated because if you follow the news, solar energy is sort of going exponential now with batteries, but that's by the by. You've got to suggest 2 reasons why potentially solar may not be the ultimate answer, just one of the solutions. Sunshine, it's not always sunny. Sunshine is not always available, it's unreliable. Solar energy might not be able to replace what else? Oh yeah, you've got to build solar farms, there might not be enough space. I don't think either of these are actually massive problems because you can use batteries for when it is sunny, but these are the sort of things that they like to answer. Let's have a little look. Oh yeah, I might have seen this question before. Sunshine is unreliable, lack of space. In the future, there will be an increased demand for energy, maybe. Solar is going to be the major solution because it's incredibly cheap now, and the batteries mean you can store the energy when it is sunny and use it when it's not sunny. But anyway, I gave 2 reasons why solar panels might not be able to provide all of the electricity. I'm doing all right here. I'm a few minutes in, I'm 12 minutes in, and I've drawn 12 marks. I need to speed up. Right, plot the data. Please don't mess up your plots. It's just embarrassing, and it's 2 free marks basically. Okay, boiling point of an alkane, number of carbon atoms in an alkane molecule 4. So boiling point 0 degrees. Put a cross on it. If you are a little bit out, you're wrong. 5 carbons, 36 degrees C. 5 carbons, 36. Right, there's 20, there's 40. Each of these is going to be 4. 4, 8, 12, 36. Takes a bit of working on that. 6 is 69 degrees C. So that's 64, 68. So there's 70, right in the middle there. That is tricky to do. You would use a pencil, please. 69 degrees C, so that's 64, 68, just above 68 is 69. 7 is X, so they're not giving me that. 8 is 126. 8 is 126, so 124, 128, that must be 126 in between. And 9 is 151. 150 is right in the middle, 151 is just ever so slightly above that. Okay, 2 marks. Absolutely ridiculously easy. Do they ask for a line of best fit? No, it says predict the boiling point of the alkane with 7 carbon atoms in a molecule. Use table 1 and figure 2. I'm just going to use figure 2. So it's going to be around about there, somewhere like that. 100 degrees C. Should we go for that? I'm not looking at the mark scheme. We're going to check in a minute. It'll give you a range. Figure 2 is not suitable to show the boiling point of the alkane with 3 carbon atoms in a molecule. Suggest the reason why. Right, because 3 carbon atoms in a molecule is going to be below 0, and my axis doesn't go that far. Will be below 0 degrees C, and what's that called? The down axis, the y-axis. The y-axis only goes to 0. My writing isn't normally this messy, it's only when I'm writing. I promise, I promise. What is the state at 20 degrees C of the alkane with 4 carbon atoms in a molecule? Alright, so that's this one. Well, it boils at 0. If something boils, here's a useful diagram for you. Things can be solids, liquids, and gases. Between a solid and a liquid is a melting point. Between a liquid and a gas is a boiling point. If something boils at 0 degrees C, at 20 degrees C, which is that way, it will be a gas. will be a gas. Below the boiling point, you're a liquid. Below the melting point, you're a solid. So 20 degrees C is above 0, so it's going to be a gas. Gas. If it doesn't ask me over the page what is the name of the alkane with 4 carbons, you'd say, I hope it asks me because it's such an easy question. What are we doing? What are we doing? Okay, table 1 is repeated below. The alkane with 9 carbons is called nonane. Complete the formula of nonane. All right, you might remember this: CnH2n plus 2, 9, double it and add 2, 20. Easy. Nonane will condense lower in a fractionating column during fractional distillation than the other alkanes. Explain why. Okay, fractional distillation. So I'm aware that most of the people watching this will be people who I teach. This is a fractionating column. Something there as well. You heat the crude oil, it evaporates, it rises up the column. As it rises, it cools, and then it will condense at its boiling point. I call this the mnemonic HERC-CAT. Heated, evaporates, rise, cools, condenses at the boiling point. This is because as you go up a fractionating column, it gets colder. It's hot at the bottom. All right. Nonane will condense lower in a fractionating column during fractional distillation than the other alkanes in table 1. Why? You should reverse the temperature gradients in the fractionating column. Nice, okay. So, hot at the bottom, column is hot at the bottom, gets colder as you go up. Again, put this into normal sentences. The column is hot at the bottom and it gets colder as you go up. Nonane has, why does it condense lower than the other alkanes? Has the highest boiling point of the alkanes in the table. So we'll condense lower. Do we need to say anything else? Hotter at the bottom, colder at the top, and it's got the highest boiling point. I think that's all I need to say. Right, 8 marks on that. I didn't say long, so let me just check the mark scheme, which I've already modelled up. I'll manage that. Right, bear with me as I just look through my mess. Alright, 2.1. The graph, all 5 points plotted correctly. Yay, definitely. Allow a tolerance of half a small square. Right. 98 degrees C, I put down 100. Allow a range in the value, allow a value in the range of 90 to 104, so I got that mark. I said, why couldn't you plot that point? I said, because of the y-axis doesn't go that low because it's lower than 0. I got that mark. I said gas. I said C9H20. I am smashing this paper. I have lost the next bit though. Why do I always lose things? Don't answer that question. 2.6. Oh yeah, 2.6. Right, 2.6. Nonane has a higher boiling point, or has a higher boiling point than all the other ones in the table. Good. It condenses where the column has a higher temperature. Nonane collects where the column has a higher temperature. Oh, did I say that? I said it will condense lower. And I did write it's hotter at the bottom, so I've implied it will condense up at where it's got a higher temperature. Is implied enough? I don't know. I'm going to give myself 1 mark, which is embarrassing, but it's true. I don't think I said it specifically enough. I think I would probably get what's called benefit of the doubt there, because I implied that it condensed where the column has a higher temperature. Alright, but I might not. That's just a fact, that's the way it is. I don't cry about it, I just get on. I know I'm going to score 90% on this. That's just the way it is. Right, next question, question 3. This question is about paper chromatography. A food colouring contains a dye. Plan an investigation to determine the RF value for the dye in this food colouring. Your plan should include the use of a beaker, a solvent, and chromatography paper. Alright, I would start off by drawing. Straight in here, I haven't really thought about it, I'm just doing it. It's a line. Oh, I'm going to put a lid on it actually. Right. What I'm going to do, I've got some chromatography paper. chromatography paper, pencil line, solvent. I'm just checking there back to say what solvent it didn't say if it's soluble in water or not. I just learned for it. So what I'm going to do here, I'm going to put it in a beaker, so I'm going to label beaker as well. I'm going to label lid. And then, right, I'm going to put my dye on here. And what's going to happen, it's going to rise up the paper. Right, so I'm going to describe this setup. Put a spot of dye on pencil line. I've already realised I should have said pencil line first. Okay, draw pencil line 1 centimetre from bottom of chromatography paper. Okay, I'm not going to write all the words, you'll have to do this. Then put a spot of dye on the pencil line. Then dip it in the solvent, but don't let the solvent go above the pencil line. I'd write that there. Okay, the solvent's got to be below the pencil line. Allow the solvent to rise near the top of the paper. So it's going to go to about there. Remove paper from solvents. Then what do you do? Okay, so now I've got this. Got a pencil line, that's where the solvent got to, and I'll have like stuff like that, won't I? I would just put one dye, so it's going to be one spot, there'll be one spot. Measure distance moved, quite a terrible handwriting, by solvent, sorry one. Measure distance moved by spot, so this distance and this distance, divide one by the other, bosh, RF done. Alright, but notice, you can start off with a diagram, that's the point. The key things they want to know pencil line, because a pencil line doesn't dissolve in the solvents. They want to know the solvent's got to be below the line, they like you to have a lid on top. Alright, normally it says a diagram is allowed, but okay, pencil line, I did that. Spot of food colour on the line, yeah. Solvent, use of a suitable solvent. Yeah, I just wrote solvent, I should have written water maybe. Yes-ish, I did say solvent. Put it in a beaker, yo. Place paper in the beaker, yeah. So the chromatography paper is in the solvent, yes. Solvent is below the start line, yes. Use a lid, yes I do. Wait for the solvent to travel up, yes. Near the top, yes. Mark when the solvent front. Measure the distance moved to the solvent, okay, didn't write that. Dry the chromatography paper, didn't write that. Measure the distance between start line and centre spot, yes. Use the measurement to determine RF, yes, I mentioned all of them. The design plan will lead to the production of a valid outcome, yes. All the key steps are identified and logically sequenced. All the key steps are, yes, I would give myself 6 for that and I've marked these papers before. That's boss. But not looking like that, obviously use sentences and make it legible. Alright, this is just me going through it quick. You're listening to the way I'm thinking about the chemistry, not actually writing it like me, because it's awkward. 2 students investigated dyeing food colouring using paper chromatography. Each student did the investigation differently. The RFs they determined for the same dye were different. How did the students' investigations differ? Right. If you used a different length of paper, that wouldn't affect it. Because if you had a paper that moved up halfway, it had an RF of 0.5 on here, it doesn't matter if you used a bigger piece of paper, it would have an RF of 0.5. Anyway, that wouldn't affect it. Different period of time used? No, it doesn't matter. If you let it run, that would not affect it. Different size of beaker? No. It's this. I don't know why I'm waffling. Different solvent used. If you use the solvent that the dye preferred or performed stronger attractions to, it would move further. You should know that when you change the solvent, you'll change the RF value. I don't know if I can explain that well, but it's just sort of an obvious question, the easiest question on the paper. Paper chromatography involves a stationary phase. Yes, the paper is the stationary phase. Now, what is the stationary phase in paper chromatography? It's the paper. The stationary phase is the thing that stays still. Yeah, the paper. The solvent is the mobile phase. The dye is the dye. The beaker is a beaker. Right, next bit of organic chemistry, polyethylene and polyesters. Polyethylene is produced from ethene. Yes, it literally means many ethenes. Figure 3 shows part of the display structural formula for the reaction. Right, very straightforward. All you do is you draw the same molecule in here, but you get rid of the double bond. Doosh, 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 doosh. Complete figure 3. This means lots of these join together to form a chain of them. You've got to put the end down there. It's 2 marks. We're going to check the mark scheme. All right. If this was a CH3, you put a CH3 there. If this was an F, you put an F there. It doesn't really matter. Right, polyethylene is a thermo-softening polymer. Thermo-softening, you heat it, it gets soft. Suggests why polyethylene is easier to recycle than thermosetting polymers. Right, the polyethylene can be heated, melted, and remolded. All right, this is the recycling topic. You heat it, you melt it, and you remold it, whereas thermosetting polymers don't melt. All right, so really, that's it. Let's have a little look. 4.2. Polyethylene melts and can be reshaped. I said remolded, so I got that. 2 marks. Heat it, melt it, remold it. Right, ethene produces different forms of polyethylene. How can different forms of polyethylene be produced from ethene? Right, this is the part in your spec that talks about high density polyethylene and low density polyethylene, and you need to know they are different forms. Like LDPE is used in plastic bags, HDPE is used in things like buckets and things like that. So how can different forms be produced? All you have to know is that you use different reaction conditions. You can use different temperatures or different pressures. You don't need details. So I'm just going to write different reaction conditions. And I'm going to find the mark scheme. And here it is. Look, different reaction conditions. You can just be as vague as that. Allow, use different temperatures and pressures, but you don't have to say how. So remember, you do need to know HDPE and LDPE. Different forms of polyethylene with different uses. Plastic bags, bins, and pots and stuff. Different reaction conditions, that's all you need to write there. Steady away. Right, the 2 different forms of polyethylene, now here we go, are HDPE and LDPE. High density and low density. Right, HDPE, notice, here's a polymer chain. There's one of the chains, there's 2 of the chains. I'm going to go over them. There's one of the chains, there's 2 of the chains, there's 3 of the chains. And notice how they're all packed together. Low density polyethylene, there's a chain. It looks like it's got these branches coming off it. Because it has got branches coming off it. Alright, explain why HDPE is a higher density than LDPE. Okay, HDPE, it looks like the chains can pack closer together. Are you noticing that? They can pack closer together. If they're packed closer together, there will be, well, what would you say, more chains per air volume, more chains in a volume maybe. So they're packing closer together. You could also, just more polymer chains in a volume is what I would go with. Whereas this one, they're not packing as closely together, so there's going to be fewer chains in a volume. I doubt I'll have to say both. I think I might say that these are branched. I like the look fact that these are branched. But anyway, let's have a look. I don't know, I've lost that already. There we go. Right. In HDPE, the polymer chains are closer together, or the molecules are closer together. So there's more atoms per volume, or more molecules per volume. Yeah. Okay. So I could say that. I waffled a bit. I could have easily got 1 there, but I didn't. I got 2. So yeah, I've only got 1 mark so far. Right. Figure 5 shows 3 monomers, A, B, and C. Monomer A can react with monomer B and with monomer C to produce polyesters. Alright, so this is one where I'm going to slow down a little bit. Monomer A. This has got an alcohol group on each end. Monomer B has got a carboxylic acid group on both ends. Monomer C has got this interesting group here, which you've not come across. It's got, instead of a COOH, it's got a C double bond O with a Cl. But it can also bond with monomer A. Okay. I've written all over this now, haven't I? Draw a circle on figure 5 around an alcohol functional group. Oh, that was annoying. Around an alcohol functional group. So imagining that I haven't just drawn all over this. like an idiot. All right, alcohol function group. If you hadn't done this in an exam, you just Googled all over it like I have, I would say alcohol functional group. I'd make sure the examiner could see that. I've got that marked there. So you have to circle the O and the H. You could have circled this one as well. But it says and, not all. So complete table 2 to show the formula of a small molecule produced when A reacts with B. Now these are condensation polymers. So when A reacts with B, what's going to happen is OH here is going to join up with an H here, and you're going to make H2O. All right? H2O will be given off because it's actually it's this one. It's H, and O get given off. In this one, it's a little bit trickier because you've not come across it before. So for you, like, it might be a bit of a guess. But what happens is H and Cl are given off. HCl. This is definitely application of knowledge, trying to work it out. So I don't expect many of you to have got that wrong, right? Therefore, I don't expect everybody to have got 1 mark here. I'm going to try and show that a little bit better. If you've got a molecule that's got an OH group on the end, and it joins onto a molecule with a C double bond O like this, the H and the Cl are kicked out, and then the molecule joins together. The one you've learned about is when an alcohol joins to a carboxylic acid and H2O is given off. So it's knowing this and then being able to guess that it's HCl. It looks like a molecule that you've come across before, hydrogen chloride. So yeah, maybe you picked up this mark, maybe you haven't. Don't fret. In an exam, don't panic if you can't get that. You've got to have a guess. I'm well into guessing. All right, this question about fertilizers. Oh, my favourite topic. That was sarcasm. Right, this question about fertilizers. Some fertilizers are described as NPK fertilizers. Nitrogen, phosphorus, potassium. Which 2 compounds each contain 2 of these elements? Okay. Ammonium nitrate. Now, okay, I'm going to look for obvious ones here. Ammonium phosphate, that's got phosphorus in, and ammonium, is NH4, so this has got nitrogen and phosphorus, that's got 2 of the elements in. Calcium chloride, nah. Calcium phosphate, it's got calcium and phosphorus. This has got potassium and chlorine. This has got potassium and nitrogen. That one. All right. The key bit to getting this is knowing that ammonium is NH4, otherwise you wouldn't have spotted that that's got nitrogen in it. Right, rocks containing calcium phosphate are treated with acid to produce soluble salts that can be used as fertilizers. Name the soluble salt produced when calcium phosphate reacts with nitric acid and phosphoric acid. Oh my god, I can't remember these sort of things. Right. Calcium phosphate plus nitric acid, I'm pretty sure, makes calcium nitrate. Now, there's a diagram. You've got to know all your salts, haven't you? Calcium phosphate with phosphoric acid. Now, this is one. What does that make? I can't remember. We had a little diagram. If you're in my class, you'll know this little diagram. Is it like triple superphosphate or something like that? I think it's triple superphosphate. Can't remember. I'm gonna guess. I think it's a salt called triple superphosphate. It's one of those annoying things as a chemistry teacher that you can't actually work out necessarily. You just have to learn. This one I worked out. Calcium phosphate plus nitric acid. It seems obvious it's going to be calcium nitrate. This one I think makes something called triple superphosphate. I will check in a sec. I will check now, because that's the back of the page. Down the balance sheet. Right, okay. Ammonium phosphate, got that right. Potassium nitrate, of course I got that right. I knew that was right. Nitric acid, calcium nitrate, yes. Triple superphosphate. Whoop, whoop. I'm doing all right. Notice though, I'm not massively bothered if I drop a mark here or there. It's not about that. It's about not messing up the massive questions. Here's a massive question. Don't mess it up. Right. Ammonium sulfate is a compound in fertilizers. Ammonium sulfate, I'm just going to do some chemistry on this. Ammonium sulfate is NH4 twice SO4. You might not know that, but I did. Ammonium sulfate can be made using an industrial process in the lab. All right, so it's a salt, ammonium sulfate. They're going to react streams of ammonia solution, which is NH3, ammonia solution, aqueous, and sulfuric acid, which is H2SO4. With ammonia and sulfuric acid will make ammonium sulfate. They're going to evaporate the water by passing the solution down a warm column. Okay, interesting. They're going to collect dry crystals continuously at the bottom of the column. So this is making salts in an industry. So what we normally do is we evaporate it in evaporating basins. They're going to pour it down a warm column and the dry crystals will form as that happens. Okay. In the lab, the following steps are used. We're going to react ammonia with sulfuric acid in a conical flask. Okay, a little conical flask. Ammonia and sulfuric acid go in there. They're going to evaporate the water from the solution until crystals start to form. So they're going to put it in an evaporating basin, probably. They're going to leave it cool and crystallize further. They're going to separate the crystals using filtration, okay, and they're going to dry the crystals between pieces of filter paper. Evaluate the two methods for producing a large mass of ammonium sulfate. Hey, what a weird question. Evaluate, okay, evaluate means to look at both of them and decide which is the best. You have to reach a conclusion. All right, I'm going to try my best. This isn't off the specification necessarily. Okay, so the first one, you've got streams of ammonia and sulfuric acid together. It's going to be continuously produced. So I'm going to say industrially, it's a continuous process. Doesn't need to be stopped. Doesn't need to be stopped and started. I think I would write that. You are continuously producing dry crystals as long as you've got streams of ammonia and sulfuric acid together, whereas in the lab you're going to have to do it one at a time. You're going to make one conical flasks worth at a time. This is actually known as a batch process, but you don't need the word batch process. It just means it has to be done, cleaned out, done again, cleaned out, done again. So I'm going to mention that sort of thing. You have to do it a little bit at a time. That means that the industrial process is going to be a lot quicker. You can do it on a larger scale, and therefore the industrial process is better for producing large masses of ammonium sulfate, which is pretty blooming obvious because it's an industrial process. Is that really it? Right, industrial process can be done on a larger scale. Is it right that? I think I mentioned it. It's quicker, it's a continuous process, and I made a reasoned judgment. The reasoned judgment being, obviously you're going to use that because you're going to make larger masses. I don't know if I'd have got 4 or 3. What a strange question. Don't like that. This question's about cycloalkenes. Interesting, because they're not in the specification. Alkene is something with a carbon-carbon double bond, like this. Cycloalkene actually means, you know, they're all joined together in a ring. Cool. Cycloalkenes are ring-shaped hydrocarbon molecules containing a carbon-carbon double bond, like I just said. Should have read that. Cycloalkenes react in a similar way to alkenes. It's going to be hydrogens all the way around there, by the way. Each carbon forming 4 bonds. All right, so describe a test for the carbon-carbon double bond in cycloalkene molecules. Absolutely double, straightforward. Bromine water turns from orange to colourless. Don't get that wrong. Don't write the word clear. Clear means no bits, colour means no colour. Right, table 3 is the name and formula of 3 cycloalkanes. Cyclobutene, bute meaning 4. Cyclopentene, C5. Cyclohexene, C6. Determine the general formula for cycloalkenes. Right, so if C is N, what do you do to get to 6? You double it, and then you take away 2. 2N minus 2, does that work? 2N, yeah, CN, H, 2N minus 2. I'm so clever. Not really. Not really. Right. Figure 6 is display formula of cyclohexene. Hexene 6. 1, 2, 3, 4, 5, 6. That's the one I drew before, isn't it? C6H10. Please notice that all the carbons have got 4 bonds coming out, and that's important. Chlorine reacts with cyclohexene to produce a compound with the formula C6H10Cl2. Right, yes, this is because alkenes can do addition reactions. So chlorine basically, actually I'll draw it like this. Chlorine comes along, Cl like that and that. New bonds form. This turns into a single bond, and you join the chlorine over the double bond like that. So you're going to end up with this molecule, or single bond. Double bond disappears. Chlorine goes there, and now what you've got to do is finish up all the hydrogens. This carbon's got 2 bonds, so there's 2 hydrogens there. This carbon's only got 3 bonds, so you need a hydrogen there. This carbon's only got 3 bonds, so you need a hydrogen there. This needs 2 more hydrogens. Make sure your hydrogens look like H's, not like that one there. Be neat. Calculate the percentage by mass of chlorine in a molecule of C6H10Cl2. What? Maths? Alright, so firstly I need to work out the MR of this. I've got 6 carbons, so that's 6 times 12. I've got 10 hydrogens, so that's just plus 10. And I've got 2 chlorines, which is 35.5 times 2. This is going to be the MR. I've got a calculator. It's not mine, I borrowed it. Slash nicked it. 6 times 12. Oh, I'll do it like this. Plus 10. Plus 35.5. Plus 35.5. 153. I probably should check that, but I can't be bothered. Right. So the whole thing weighs 153. Surely that's going to get me a mark. So the percentage by mass of chlorine, how much of that 153 is chlorine? 35.5 times 2. So 71 out of the 153 is chlorine. 71 divided by 153 equals times 100. 100 equals 46.4. I think I'll look for that 46.4. We could probably get away with 40. Let's have a look. 47. What's it? 151. 46.4. Look, I don't got it right. We're near the end yet. It's taking ages. Right. Potash aluminium is a chemical compound. It's a funny looking chemical compound. It's got 2 metals in it. Potash alum, sorry. KAlSO4. It's got potassium, aluminium, and 2 sulfates. Give a test to identify the group 1 metal in potash alum. Group 1 metal is potassium. What chemical test do you know? Flame test. Right, I'm going to do a flame test on the potassium. Lilac flame. I like the colour of this pen that I've also nicked. Lilac flame. Just give a test. Now, I might just write flame test. Firstly, I'll write flame test, and then I'll describe it. Put a sample into a blue flame on Bunsen. Right, that what I had to write? Question 7. Oh, I could have just written flame test or allow description of flame test, lilac flame. Right, name one instrumental method that could identify the group 1 metal ion. Right, loads of triple students forget this. Flame emission spectroscopy. It's an instrumental method that does like really cool flame tests. Flame emission spectroscopy. All right, FES. I'm just being lazy. All right, look it up. If you didn't know that, look it up. It's not hard. It would not only identify the group 1 metal, but show you how much you've got. Really, really clever. Right then, the student identified the other metal in potash alum. Oh, that was aluminium, wasn't it? They added sodium hydroxide solution until a change is seen. Give the results of this test. If you add sodium hydroxide with aluminium, you get a white precipitate forming, which then dissolves in excess. All right, that's how it is. Okay, white precipitate. Yeah, ignore that it dissolves. Ignore just means you can write it, but it gets ignored. But I said that. I should get 2 out of 1, but that's not a thing. White precipitate. This test gives the same result for several metal ions. Yes, it does. Aluminium gives a white precipitate. Calcium gives a white precipitate. And magnesium gives a white precipitate when you add OH-. They all do. What additional step is needed so that the other metal ion in potash can be identified? Oh, this is why they didn't want it up here. Give the result of this additional step. Add excess sodium hydroxide, NaOH, sodium hydroxide, because it's written that. Results, the precipitate dissolves. I know that's right. I'm very good at ions tests. I'm really modest. So, describe a test to identify the presence of sulfate ions. Oh, these are so easy. The test for sulfate ions is you need hydrochloric acid and then barium chloride. You need to know your ions tests. Hydrochloric acid and barium chloride, and you will get a white precipitate. The white precipitate is barium sulfate, by the way. Easy. Question 8 is a question about copper and alloys of copper. Solvers are alloys that are used to join metals together. Some solvers contain copper. Remember, alloys are mixtures of metals. Table 4 shows information about 3 solvers. Some of you will have done soldering in school. So solvers are alloys used to join metals together. Some solvers contain copper. All right. Table 4 shows information about 3 solvers, A, B, and C, and it's got their melting points. Tin, copper, and lead. Tin, copper, and silver. Tin, copper, and silver. Okay, so B and C are similar, but not quite the same. Solder B and solder C are now used more frequently than solder A for health reasons. Suggest one reason why. Solder A's got lead in it. Lead is toxic. That's just general knowledge. Lead is toxic. Suggest one reason why solders B and C have different melting points. Okay, I'm imagining, even though they're made of the same elements, they are going to be mixed in different ratios. So I might write different mixtures or different ratios or different quantities of tin, copper, and silver. That sort of idea. Let's have a look. 8.2. Different proportions. Yeah, absolutely. 1 mark, 1 mark. Right, copper can be obtained by processing copper ores, recycling scrap copper. Suggest 3 reasons why recycling scrap copper is a more sustainable way of obtaining copper than processing copper ores. Right, to process copper ores, you need to dig them out of the ground. You need to then separate the rocks, so you need to process them, which takes loads of energy. You then got to extract or reduce them with carbon. Oh, it's loads of energy. Right, processing copper ores takes loads of energy. Copper ores are non-renewable, whereas recycling scrap copper takes less energy, and you're using copper that has already been extracted. I'm just trying to find the mark scheme here. Right. Any 3 from. It conserves copper ores. Recycling uses less energy. Recycling reduces waste. Reduces use of landfill. I didn't mention that. It reduces the mining or the quarrying or the environmental impacts. Did I say this very well? I don't think I did. Okay, uses less energy. I did say that. Non-renewable. Non-renewable. I didn't say that it reduces the use of landfill. You know what? I've only got 1 mark for that. Sad face. I am rushing though. I think I'd have done better. Right, what do you need to say? Recycling conserves copper ores, so remember that in case it comes up in 2025. Recycling uses less energy, so I got that, okay. Recycling reduces waste. I didn't say that. I implied it, but I didn't say it. Mining or quarrying causes environmental impacts. I didn't say it. No, I'm definitely still a sad face. Oh man. So how many marks have I dropped? 3? Done alright, I'm still going to get a 9. Do you know you can drop 28 marks out of 100 and still get a level 9? I'm cruising. Absolutely cruising. That's what you've got to think like. Right, okay, surely I'm near it again. Copper is extracted from low-grade ores by phytomining. Phytomining means plant mining. Bioleaching means bacteria. See, phyto, plant, bioleaching, bacteria. Describe how copper is extracted from low-grade ores by phytomining. Right, you plant a load of plants on top of the low-grade ores. You let them grow. That means it's going to take some time. So they've got to grow. Then you harvest. Then you burn to create an ash. Then, from that ash, you need to typically add an acid. All right, so you're going to add an acid. and then extract using scrap iron. God, I think I remembered all of that. Let's have a look. Okay, grow plants. Plants to burn to produce an ash. Dissolve them in acid. And then either electrolysis or displacement using scrap iron. Cool. I'd probably mention electrolysis as well. Revised phytomining and bioleaching. Phytomining has not been widely used to extract copper. Suggests 2 reasons why. And you can't get right because it sucks. It does actually suck. It's like really, really inefficient. But 2 reasons why. It takes a lot of land, and that land isn't available. All right. The demand for what else would I say? Yeah, new technologies have come up, I suppose. Better technologies have come up. You've still got high-grade ores out there. Really, it takes a lot of land. I suppose really, if you want to have a go to it, it takes up a lot of land, and it takes a heck of a lot of time. It's slow and it takes up loads of land. Answers. There are still high-grade ores available. Didn't say that. Land is not available. I said it takes up a lot of land. It takes a long time. Yes. Okay. Phytoman is rubbish. Nice idea, but not really good. Right, a student investigate how changing concentration affects the rate of reaction. So this is a rates question. Is this the last question? Please say it is. No, it isn't. Right, zinc, sulfuric acid, zinc sulfate and hydrogen. So they're gonna put some sulfuric acid into a conical flask. There it is. They're going to add zinc powder in the top, yeah. They're going to put the stopper in the conical flask, yeah. And they're going to measure the volume of gas collected every 30 seconds. So the gas is going to push this plunger out, and you're going to read the volume off here. They're going to repeat steps 1 to 4 with sulfuric acid concentration of 0.1, which makes me now read this again. So the first experiment is going to be done with 0.05 moles per decimeter cubed, and the second experiment is going to be with a higher concentration, because they are investigating how changing the concentration affects the rate. All right, notice they're going to start off with a low concentration, then they're going to do a higher concentration. The student made an error in setting up the apparatus. Yeah, this pipe should not be in the liquid. The pipe should be above the liquid. Right, I believe you mark 1 line. Next, the student corrected the error, and this is the result. Okay, so what we've got here, 0.05 moles of sulfuric acid. So what happened is, at the low concentration, the reaction went bubble, slow, stop. The 0.1 mole, the more concentrated, went bubble, slow, stop. All right. Why do the lines of best fit become horizontal? Well, horizontal means the reaction is stopped, and reactions stop because the limiting reactant runs out. So no more gas is produced. All right. The delivery tube is in the acid. The reaction is stopped. A reactant is used up. I would please say the limiting reactant is used up. I've got 2 there. I'll just figure 9 show that the zinc powder reacts more slowly with 0.05. The gradient is less steep. All right, this is more steep. The gradient is less steep. That must be the answer. Yeah, less steep. Cool. We're doing all right. Question 9 is easy so far. Determine the rate of reaction for 0.05 moles per decimeter cube at 80 seconds. I'll just do that on the floor. Got to pick it up. Right, at 80 seconds. I shouldn't have scrolled all over it again. Determine the rate of reaction at 80 seconds. At means tangent. Right, okay, got to get a ruler out. I haven't got a ruler. I'm going to use a thermometer. Proper chemistry teacher, don't I? Right, at 80 seconds, 0.05, so that's a thick line. 80 seconds, 50, 60, 70, 80. 80 seconds there. Going to draw a tangent line like that. And now I need to draw a triangle on that tangent line. I'm going to work out rise over run. Okay. 1, 2, 3, 10, 20, 30 seconds. No, 30 centimeters cubed. I'm getting tired. And this is from here to here. That's 50 seconds, 100 seconds, 150, 160, 100, 150, 160, 170, 180. 180 divided by 30, centimetres cubed divided by seconds, 30 divided by 180, 30 divided by 180, calc, 0.16666 centimetres cubed per second. Now that has got to be, two sig figs, 0.17, 2 sig figs rate of reaction. I'm just taking my time here, just in case I make a silly mistake. It's going to be 30 centimetres cubed divided by 180 seconds. 50, 140. Yeah. All right. Mark scheme doesn't give me a number, you see. It just says tangent drawn, I drew it at 80, did that. Value for the x step, I worked that out as being 180. Y step was 30, y over x. I did do y over x, didn't I? Yeah. Calculation of rate, yeah, 2 sig figs. Please notice, 5 marks for being careful. Even me, in this point, I was a bit more careful there. Right, the activation energy for the reaction between zinc and sulfuric acid is lowered if a solution containing metal ions is added. What's the most likely formula of the metal ions? This is knowing to lower an activation energy into catalyst, and in triple chemistry, catalysts are transition metals, so you choose the only one of them to transition metal. That's group 3, that's group 2, that's group 1, that's transition metal. Right, question 10. This question is about alkenes and alcohols. Alkenes are C11C, alcohols have got COH, they've got an OH group. Ethene is an alkene produced from a large hydrocarbon molecule, yes, by cracking. Large hydrocarbon molecules are obtained from crude oil by fractional distillation. Name the process used to produce ethene from large hydrocarbon molecules. Cracking. 1 mark. Describe the conditions used to produce ethene from large hydrocarbon molecules. Right, cracking, there's 2 types now. Is it steam and thermal in A level? So in GCSE. So either way, so steam or catalytic, isn't it? So it's high temperature. You can't just say heat. You're not allowed to say heat. I remember this. High temperature, high temp, and you can have steam, or you can have catalyst, depending on what you want. I know they're right. I'm not even going to check. I just remember once in front of the class writing heat and getting no marks. You have to say high temp. All right. 10.3, ethanol can be produced from ethene and steam. I'm seeing a little reversible arrow. The forward reaction is exothermic, so write exo in that way and then endo in that way. Do that first every single time with a reversible arrow. This is going to be Le Chatelier's principle. Explain how the conditions for this reaction should be chosen to produce ethanol, this stuff, as economically as possible. All right, what I want to do is I want to shift this equilibrium to the right to make as much of this as possible. All right, so I'm going to firstly talk about temperature. Right, with temperature and Le Chatelier's principle, this is useful in N. If you increase the temperature, it shifts it in the endothermic direction. So, if you increase the temperature, it'll shift it that way, and you will make less ethanol. So really, low temps shift the equilibrium to the right in the exothermic direction, making more ethanol. But low temps mean a slower reaction. So I'm going to use a compromise temperature. So a compromise warm temp should be used. I don't know the mark scheme, I'm just guessing. Blood temperature, pressure. Right. Pressure. Right, there's 2 moles of gas over here. There's 1 mole of gas here. If I increase the pressure, it will shift to the side with the fewest gas moles. I'm going to say use at high pressure because I'm running out of time. Because if I increase the pressure, it will shift to the side with the fewest gas moles in order to oppose the change. Okay, I'm going to use a high pressure. Notice 2 moles of gas, 1 mole of gas. I'll write all of this in, 2 moles of gas to 1 mole of gas. I'm going to go all over, I'm going to go big on this. I would use a high pressure. All right, I'm also going to say, but not too high, because high pressures cost muchos dinero, cost a lot of money, so I'm going to go mid pressure. High, but not too high. All right, what else am I going to do? I'm going to use a catalyst. Catalyst, it's going to speed up reaction. Doesn't get used up. Not used up. What else about a catalyst? So lowest cost, because you don't need. What else? Yeah, you don't need as high. Yeah, you don't need really high temperatures for speed. Yeah, you don't need to increase the temperature for speed, so it lowers the cost. I think I'm done on that. Temperature, pressure, catalyst. So I'm going to use a compromised temperature. I would use a low temperature, ideally, but low temperatures are slow. So I'm going to use a low temperature, increase the yield. So I'm going to use a mid temperature to get a good yield and reasonably fast. Pressure is going to be favoured by a a high pressure. Increase the pressure, it'll shift to the side with the fewest gas moles. That means you're going to make more ethanol and it's going to be faster. I'll add this in now. Faster, because higher temperatures are faster, because you get more frequent successful collisions. I'm going to throw everything at that. Right, let's have a look. Higher temperature gives a higher rate. I did say that. I didn't write more frequency. I did. I mentioned it. No. So I think I would need to write, it's a rates question. So make sure you mention collisions. Higher pressure gives a higher rate. I did mention that one. Because more frequent successful collisions, I did mention that. A catalyst can be used to give a higher rate. Yes, you're going to make it faster because the activation energy is reduced. Yes. Yield. A higher temperature gives a lower yield. I wrote a lower temperature gives a higher yield, so I'm doing that. Because the reaction is exothermic, yes. A higher pressure gives a higher yield, yes. Because there's more molecules on the left-hand side, yes. I said 2 to 1. High temperatures use more energy, so costs increase. Didn't mention that. High pressures use more energy, I did mention that. Higher pressures require stronger reaction vessels, so cost increase. I didn't mention it, but I definitely would have, but I didn't. Compromise, I did mention a compromise. The chosen temperature is a compromise, yes. The chosen temperature is a compromise between rate and cost, yes. Chosen pressure is a compromise between rate and cost. I did mention that the pressure is a compromise because high pressure. Yeah, I did write just in error. I did say that. I did write that. I'm 100% getting 6. You don't have to hit all of the points. Relevant points, I are identified, given in detail, logically linked, yes. At the worst, I'm getting 5. I'm definitely getting 6. Right, ethanol can be produced from sugar solution by adding yeast. Name this process, fermentation. I have to say that. Butanol, 4 carbons, can be produced by sugar solution by adding bacteria. Sugar solution is broken down in similar ways by bacteria and by yeast. Suggest the reaction conditions needed to produce butanol from sugar solution by adding bacteria. Right, bacteria, living creatures. I want to do about 37 degrees C. Sugar solution is broken down in similar ways by bacteria and yeast. Okay, so I know sugar solution is broken down by yeast at 37 degrees C and anaerobic. I'm going to go for that. That's my guess. 10.5 anaerobic. Oh yeah, tick, warm anaerobic fermentation. Marking this. Right, you're not going to get 100%, but you're going to get pretty close. Okay, this is like a random help. A car needs an average of 1.95 kilojoules of energy to travel 1 meter. 1 meter, 1.95 kilojoules of energy. Ethanol has an energy content of 1,300 kilojoules per mole. So a mole of ethanol releases 1,300 kilojoules. Calculate the number of moles of ethanol needed by the car to travel 200 kilometers. All right, I'm going to turn 200 kilometers into meters. I've got 200,000 meters. I know that 1 meter equals 1.95 kilojoules. So if I times that many meters by 1.95, I will work out how many kilojoules I need. 200,000 times 1.95. I'm going to get what I need 390,000 kilojoules of energy to so that many kilojoules for 1 meter, this many kilojoules for that many meters. So I need this many kilojoules of energy. All right. I know that 1 mole of ethanol is 1300, so basically nowhere near that amount. If I divide this number by 1300, I should get the number of moles. Notice if it was 1300 divided by 1300, you'd need 1 mole. I'm taking the big number divided by the small number. Divided by 1300, 300 moles. Yeah? If I messed that up, I'm so tired now. You know, this is taking me well longer than I thought. 10.7. Can't even find the mark scheme. 10.7. 300 moles. I'm not trying to explain it, I just sort of winged it. When butanol is burned in a car engine, complete combustion takes place. You're going to make carbon dioxide, right, and water. Write a balanced equation for the complete combustion of butanol. Butanol? Has it given me butanol? I mean, I know butanol, but has it given me butanol formula? Can't remember if it has. 10.6. God, I've lost everything. 10.5. Butanol? No, it's not. Right, butanol. It's just one of those ones you need to know, isn't it? But is 4. Ol means OH. Everything else must be hydrogen. So I'm just doing a little bit of working out. All right, C4, H9, OH. All right, C4H9, OH, or you could have written it C4H10O, but this is better. They're keeping me OH separate. I'm going to combust it, I'm going to react it with oxygen. I'm going to make CO2, because it's complete combustion. I'm going to make H2O. 4 carbons, 4 carbon dioxides, 10 hydrogens, 5 H2Os. Got to go back and balance my oxygens now. There's 8 oxygens here, 5 oxygens here, so there's 13 oxygens on this side. There's 1 oxygen here, a number 6 in front of that will balance it. There's now 13 oxygens on this side. I'm smashing this paper. I reckon I've scored 98%. I hope that wasn't too shambolic, but just go for it. Just go for it. Like, just how messy my everything is now. This is what it looks like. Seriously. Just wanted to realise. What a shambles. Hope you enjoyed. Hope it's useful. Bye.